Back when you were little, your teacher probably told you to line up in perfectly straight lines and walk in a certain order. Now, you're probably much older and freely go from class to class. In Bohr models, we're taught that electrons kind of go around the atom, much like planets around the sun. But in reality, electrons take a much different organization, and this is what we call electron configuration. It's actually impossible to know 100% where these electrons are going to be, but we can have an idea of where they'll be based on the atom they're a part of. Let's put this into perspective of something you'll be familiar with, a grocery store. If I go to a grocery store and I'm in need of, let's say, cereal, I'll probably go to the cereal aisle of the grocery store and expect to find my cereal there. But sometimes cereal can be found other places too. You may walk into produce and see a box of cereal next to some tomatoes or bananas. While that's not the expected place we would see cereal normally, it doesn't mean it can't happen there. Sometimes cereal can just be in places we don't expect them. However, that 99% of the time, we're going to expect it to be on the cereal aisle. And this is how we think about electrons and their energy levels. Each energy level has orbitals, or areas of probability. Like the aisle in the grocery store, this is where our electrons are most likely to be. But again, there can be electrons in some random one-off spot that we didn't expect it. The first type of orbital we can have is known as the s orbital. This orbital can hold only 2 electrons. The next type of orbital is called the p orbital, which can hold up to 6 electrons. The third type is the d orbital, which can hold up to 10 electrons. And lastly, the f orbital, which can hold up to 14 electrons. So how do we use these orbitals to describe an atom? We look at the periodic table. As we discussed in a previous video, the basic structure of the periodic table, at least for periods, is that the number of period the atom is in, that also equates to the number of energy levels that atom is going to have. When we're writing an electron configuration, this is the first thing we'll look at. For example, lithium is in period 2, so it will have 2 energy levels. The next step is to identify the sublevels that we're in. To do this, we read the periodic table much like a book, left to right. In general, this is how we would read through the periodic table. Starting with hydrogen, we are in period 1 and have 1 electron total. We can see the group 1 is part of the s block. So when we're writing the electron configuration for hydrogen, we would say 1s to the 1 because it's in the first period and has 1 total electron that can fit in that sublevel. So before we head off into other examples, let's take a look at some rules and principles that'll be helpful along the way. The first principle is known as the Aufbau Principle, which states the electrons fill the available orbitals from lowest energy to highest energy. In the ground state, all the electrons are in the lowest possible energy level. This is like saying if you were running a hotel, you would have to fill up the entire first floor, then the second floor, and nobody could be any higher until all the rooms were filled. The next rule is known as Hund's rule. The electrons must be placed into the orbitals in a way that no pairs are put together unless absolutely necessary. This is, single electrons must be placed into boxes first and then paired up if necessary. This is like saying if we were on a bus, each seat had to be filled with 1 person before 2 people could sit together. And lastly, we have Pauli Exclusion Principle, which states that electrons come in 2 varieties based on the direction they're spinning. There's an upspin and a downspin. Upspin and downspins are always paired together, and up and up or down and down combinations are not allowed. This is like saying if we were making soup and the recipe clearly states all the same vegetables cannot go in, but a variation can. A combination of them is fine, but only put 1 in and you'd be messing up the recipe big time. So in summary, the Aufbau Principle says we must fill up the lower energy box first before moving to a higher energy box. Hund's rule says we can have no pairs until singles find a box in the same level first. And Pauli Exclusion Principle says we can only have opposite spin states of electrons in the same box. Now that that's out of the way, let's look at some examples. The first element we're going to look at is sodium. Sodium is number 11 on our periodic table. When writing electron configurations, you're always going to start with the 1s block. This has hydrogen and helium in it. Basically, like I said earlier, you're going to read this like a book left to right. So after we're done with the 1s section, we're going to go to the 2s section, and so on and so forth, until we get to our element. In this case, sodium will have 1s2, 2s2, 2p6, and then we'll finally end up at sodium, which is at 3s1. Our next example is going to be nitrogen. Go ahead and pause the video if you want to try it first on your own. Just like with sodium, after the 1s block, we're going to move to the 2s block. And then from there, we'll go to the 2p block. Since nitrogen is number 7 on the periodic table, we actually end in the middle of the 2p block. If we don't fulfill all of the elements in this 2p block, we're going to put it to the number that we do fulfill. So in this case, nitrogen would be 2p3. Our next example is nickel. Nickel is going to end up in the D block, which is something that we haven't encountered yet. So we'll still go through the 1s, 2s, 2p, 3s, 3p, and 4s orbitals, and we'll end up in what's known as the 3D block. So let's talk a little bit about why this is. Why do we go from 4 to 3? Keep in mind Aufbau's principle. The lower energy level must be filled first. Using this arrow guide, we can go from 1s to 2s to 2p to 3p and so on, kind of following an arrow line. After we get from 4s, we go to 3d. 3d is a lower energy level than 4p, which is why we have to fill it up first. If we go back to nickel, its full electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. The last example we're going to look at today is using copper, and specifically we're going to use this electron configuration in what's known as noble gas notation. So instead of writing all the sublevels that we've been writing, we're going to start with the closest noble gas. Since copper is number 29 on the periodic table, we are going to use the noble gas argon to start our electron configuration. We'll write in parentheses argon, and then from there continue as normal. So we'll have Ar, 4s2, and then 3d9. If you found this helpful, subscribe to my channel to discover more lesson videos.